So we have already seen what is big O notation used for analyzing the algorithm. Now let's discuss what is big omega notation. So let f of n be the function that represents the running time or the time complexity of an algorithm where n is the input size. Then if we can find one another function g of n such that f of n is greater than or equal to c into g of n for all values of n greater than or equal to n naught, where n naught is greater than or equal to 1 and c is a constant which is greater than 0, then we can say that f of n belongs to big omega of g of n. That is, consider the same function f of n equals 6n plus 3. This is the graph corresponding to the function. Now, if we can find one another function g of n and a constant c such that the curve c into g of n moves along this path. So here we can see for all values of n which is greater than or equal to one particular value n naught, the function f of n is always greater than the function c into g of n. So for lower input size we don't care when the size of the input crosses a particular limit, and when it increases beyond a particular limit, then always the function f is increasing at a faster rate than the function c into g of n. It means the function f of n is never better than the function c into g of n. In other words, g of n is acting as a lower bound for the function f of n. In such case, we can say that f of n is big omega of g of n. Let's consider an example. Let f of n equals 6n plus 3 itself. Now we are going to check whether a function g of n equals n can act as a lower bound for the function 6n plus 3. In the previous video, we have already seen that the function n can act as an upper bound for the function 6n plus 3. That is, we can represent 6n plus 3 as big O of n. Now we are going to check whether we can represent the function 6n plus 3 as big omega of n. That is, whether the function n can act as a lower bound for the function 6n plus 3. For that, we know the value of n naught should be greater than or equal to 1. Let's take the minimum value. Let's consider n naught is equal to 1. If n naught equals 1, what is the value of f of 1? 6 into 1 plus 3, it is 9. And the value of g is g of 1, it is 1, 9 and 1. Now what should be the value of the constant c here such that the function f is greater than c into g of n? Even if c equals 1, then the condition is satisfied. F will be greater than g. So let's take n naught as 1 and c as 1. Now we have to check whether the function f of n is greater than or equal to c into g of n for all values of n greater than or equal to n naught. That is, whether 6n plus 3 is greater than or equal to 1 into n, that is n, for all values of n greater than or equal to 1. Let's subtract n from both sides. Now 5n plus 3 is greater than or equal to 0, where n is greater than or equal to 1. So n is having a value which is always greater than or equal to 1. So it is sure that the left hand side will always be greater than the right hand side. Anyway, let's check with some inputs. Let n is equal to 1. What is the value of f of n? F of n is 6 into 1 plus 3, it is 9. What is the value of c into g of n? It is 1. So here f of n is greater than c into g of n. Now let the size of n be increasing. Consider a higher value. Let n is equal to 5. What's the value of f of n? It is 6 into 5 plus 3, 33. What is the value of 6c into g of n is 5. Here also the function f is having a higher value than the function c into g of n. Again, the size of input is increasing. N equals 100. Now f becomes 603 and c into g of n is only 100. Here again, the function f is having a higher value than the function c into g of n. Now if we check for any value which is higher than this, as the size of the input increases, the function f will be increasing at a higher rate than the function c into g of n. That is, if the function 6n plus 3 is represented as a curve like this, the function c into g of n, where c is equal to 1, that is, the function n curve moves as this. Here, for all values of n which is greater than or equal to 1, the function f is having a higher value than the function c into g of n. That is, the function f is increasing at a faster rate than the function c into g of n. To make it simple, the function n is acting as a lower bound for the function 6n plus 3. Hence, we can say that the function f of n belongs to big omega of g of n. So in the previous video, we have seen that if one function is acting as an upper bound for a function, then any higher functions will be acting as an upper bound for the same function. Now here also the same, if one function is acting as a lower bound, then any function lower to it, any lower function will be acting as a lower bound for the same function. So let's take a lower function, that is, consider g of n is equal to log n. We are going to check whether this function log n can act as a lower bound for the function 6n plus 3. That is it possible to represent 6n plus 3 as big omega of log n? So we are considering n naught as 2. If n naught is equal to 2, what should be the value of constant c here such that the function f of n is greater than c into g of n? Even if c equals 1, f will be greater than g. Thus, we can take n naught as 2 and c as 1. Now we have to check whether the function f of n is greater than or equal to c into g of n for all values of n greater than or equal to n naught. That is, whether 6n plus 3 is greater than or equal to 1 into log n, that is log n, for all values of n greater than or equal to 2. N is always greater than log n, so of course the left hand side will be greater than the right hand side. Check with some inputs. Let n is equal to 2. What is the value of f of n? It is 15. What is the value of c into g of n? It is 1. Yes, the function f is greater than the function c into g of n. Now the size of input is increasing. N equals 16. What is the value of f of n? 6 into 16 plus 3, it is 99. What is the value of c into g of n? It is 1 into log 16, it is 4. Here also the function f is having a higher value than the function c into g of n. Again, let's increase the size of the input. N equals 2 to the power 10, that is 1024. What's the value of f of n? It's 6147. And what's the value of c into g of n? It is only 10. Here also, f is having a higher value than c into g of n. So as the size of the input is increasing, the function f is always having a higher value than the function c into g of n. So if we represent it as a graph, the function 6n plus 3 can be represented as a curve. Now, c into g of n, that is 1 into log n. Before that, the function n can be represented as a curve like this. Now the function c into log n, 1 into log n, can be represented as a curve, again a lower bound for the function f of n. So here, for all values of n which is greater than or equal to one particular value, the function f of n is always having a higher value than the function log n. So 6n plus 3 function is increasing at a very faster rate than the function log n. So log n can also act as a lower bound for the function 6n plus 3. Hence, we can say that 6n plus 3 belongs to big omega of log n. Thus, we have seen that if n is acting as an upper bound for this function, any higher function, n log n square, n cube, n to the power 4, all these higher functions can act as an upper bound for the same function. That is, if big O of n exists, then big O of n log n exists, big O of n square exists, big O of n cube exists, and so on. Similarly, if n is acting as a lower bound for this function, any lower function, that is log n, log of log n, all can act as a lower bound for the same function. That is, if big omega of n exists, then big omega of log n exists, big omega of log n exists, and so on. But if we observe the graph, we can see that here one function is acting as both the upper bound and also the lower bound. The function n is acting not only as the upper bound but also as the lower bound, but for different constant values. Here c equals 10 and here c equals 1, but the same function is acting as the upper and lower bound. In that case, we use the term tight bound. So here we can say that the function n is a tight bound for the function 6n plus 3. And the notation used for the tight bound is big theta notation. So what is big theta notation? If we have a function f of n that represents the time complexity of an algorithm where n is the input size, then if we can find one another function g of n such that f of n is big O of g of n and f of n is big omega of g of n. That is, the same function g of n, if it is acting both as the upper bound and also as the lower bound, then we can say that the function f of n belongs to theta, big theta of g of n. That is, the function g of n is a tight bound for the function f of n. It means for a function f of n, if we can find a function g of n such that for all values of n which is greater than or equal to one particular value n naught, f of n is less than or equal to c1 into g of n and f of n is greater than or equal to c2 into g of n, then we can say that f of n is big theta of g of n. That is, f of n is less than or equal to c1 into g of n and f of n is greater than or equal to c2 into g of n for all values of n greater than or equal to n naught, where n naught is greater than or equal to 1 and c1 and c2 are different constants which is greater than 0. Then we can say that f of n belongs to big theta of g of n. But the difference is, we have seen that if n is acting as an upper bound, then all higher functions can act as an upper bound. That is, if big O of n exists, big O of n square, n cube, and so on exist. Similarly, if big omega of n exists, big omega of log n exists, and so on. But that's not the case with tight bound. If big theta of n exists, it doesn't mean that big theta of n square exists, big theta of n cube exists, and so on. That is, if one function is acting as a tight bound for a particular function, it doesn't mean that any higher function is acting as a tight bound or any lower function is acting as a tight bound. So we have discussed the asymptotic notations big O, big omega and big theta which are used for analyzing the algorithm. Next we shall see how to analyze an algorithm in the three cases, the best case, worst case and the average case using the asymptotic notation.